Hey folks, Doug Blake with Body Design University. Welcome to another weekly study. And today in this video, although it's not the highest priority chapter, it's an important chapter to understand, especially if you're going into the real world of personal training, actually working with folks. It's chapter 8, exercise metabolism and bioenergetics. Yeah, ironically enough, not a ton of questions are going to come from what appears to be a really important chapter when it comes to dealing with exercise and elements related to intensity and fuel use, things like that. You would think that it would have more importance, but nevertheless, it's still an important chapter. And it's not like you're not going to see any questions. You will see. Most of them are going to be related to the amount of time that the ATP PC system lasts, 10 to 15 seconds, whatever the case is. But from my perspective, it's one of the most interesting because one of my areas of study that I've done for many years, which is exercise metabolism. So bioenergetics is just part of the, part of that sort of academic world that it's very interesting. And so what I'm going to do is I've got one slide, and it's really just one slide on, let me see what I put on there for you. It was on page, in your 7th edition, page 232, figure 8.3. That's what I'm going to bring up a little bit. And I'll just draw a couple of things here for you. But I wanted to target it because there's always questions that are being asked about the energy systems. And because it is a fairly academic subject matter, we want to make it as simple as possible, as easy to understand as possible. And in a sense, NASM really did a pretty good job of doing that, of kind of simplifying it enough so that you can understand, short, intermediate, long-term fuel usage and substrates. But what I have found is that there is this one chart or figure 8.3, energy system usage during intense exercise, that tends to throw some people off. And look, it's like any figure or any chart that you see, any drawing, the editor or the people that put this particular chapter together, they're pretty smart folks. So for them, they go, oh, this is easy piece of cake to understand. We're going to make it as simple as possible. Well, maybe. And sometimes not so much. Because the folks that ask me this question, I don't understand that figure. Can you explain it to me? As soon as I get that, I have to wonder, why is it difficult to understand? I mean, it took me, even when I first opened a book, it took me a second to go, oh, okay, got it. Right. Now I know what they're talking about. And I've been studying this stuff for years. So versus, figure 8.3 versus figure 8.4, which basically just shows the ATP PC, the creatine phosphate, adenosine diphosphate molecules. Simple to understand, easy to understand. As you continue through this chapter, you're going to get through some fairly, I'm not going to say super sophisticated. It's not, but it's sophisticated enough to where if you're not used to looking at this stuff, it could be a little, you go, whoa, that's a lot of material. Actually, it's not. And it's fairly straightforward to understand. And that's what I want to go over with you, is kind of hone in on this one particular figure. Because if you can get this, if you kind of figure this out and understand it, not just through the reading, but also just sort of intellectually understand and appreciate what's going on here with the 3 major energy systems in the bioenergetic catalog, so to speak, it's really very helpful. And you can actually use it in the real world when you're actually training people. But before I do that, real quick, when you open up chapter 8, Introduction to Exercise Metabolism, do yourself a big favor. Write this stuff down. Write it down, read it, write it, draw pictures. Okay. I say it over and over and over. You've got to rewrite the material, even if it's just written material. If you want, if you need to draw it, I would highly recommend you draw it. Use colored, thicker markers, thinner markers, whatever the case is, to help you to memorize the information. But introduction of first law of thermodynamics, not that big of a deal. Fuel for energy metabolism. That's one of the big things that I want you to write down. You grab yourself a sheet of paper and you write these down. Fuel for energy metabolism. That's basically how you would do it. You just write that down at the top of your heading, and then you would say glucose and glycogen. How is glucose and glycogen being used? They'll give you a couple of paragraphs here, tell you through anaerobic, right, processes, and then free fatty acids, which is only going to be used through aerobic processes. Amino acids, right, through the urea cycle. How much do you need to know about this? It's not that difficult to memorize what they have in here for you, the main concepts. Third fuel source, protein. So amino acids, like I say, through the what's known as the urea cycle. And then one thing I like is that they put in ketone bodies. This is really important because in today's world, you're going to be training people that are on the ketogenic diet. Okay. I don't recommend it. None of us really in your right mind is going to recommend that you put people. No, don't be messing with that. It's not sustainable for the average person. I'm not saying it's not useful and functional. It can definitely be that. The point is that ketone bodies, they're going to definitely want you to know the reasons why the body will use ketone bodies as a low, moderate, then predominant source of fuel. And that's what's going to be in there for you. And that's the only reason why I even went into that as an introduction. I just want you to know that those are, if you're going to memorize the things in this chapter, those are some pretty, on the higher end of importance. Again, keep in mind that they've given you the definitions. This is where reading, rewriting it over and over, so you got the definitions down pat. A lot of this information, ketosis, exogenous ketones, insulin resistance, this is stuff you ought to know just in general, passing the test or not. So now you get into energy systems, and they're just going to explain to you the adenosine triphosphate molecules. Just remember, ATP, it's the source, the molecular source of energy for life on Earth. Okay, it's the ATP molecule. It's because it has this high energy phosphate bond on the between the second and third phosphate component on that adenosine backbone, so to speak. And so you've got 3 phosphate groups. Between the second and third phosphate is what's known as a high energy phosphate bond. It just releases a lot of energy when it's broken, blah, blah, enzymes, yada, yada. Just read their stuff, okay? But it's really here in figure 8.3 that's important. So let me go ahead and pull this up so we can have a better look at it. Energy systems intro. That's really what we're talking about today, is just an intro to energy systems. And I wanted to bring this up because one of the most important things you can, and I'm going to use the highlighter here. And if you look, I can actually kind of wrap around here. I hope you can see this. Although it's yellow, maybe I should have used a different color. Okay. Let me go ahead and get a different color on here. There we go. So if you notice, I'm circling these little circles. Why am I circling the circles? Why? Because this is what students have said to me. Why is the circle located right here and right here and right here? Why are they located there? I don't know why they located them right there. The point is let me get rid of these. The point is that all those circles are representing, folks, is the line. Let me say that again. All those circles are representing is the line. Okay. So if you see my laser pointer now, short-term energy systems, again, this is where it can be a little confusing, and I want to clarify what figure 8.3 is telling you. If you look on the y-axis, it says percent capacity of energy systems. Any of the 3 energy systems have either 0 capacity, they're not being used at all, or 100% of the energy being produced for an intense exercise is being used by that energy system. I hope that makes sense. So all this is saying is that this orange line represents the ATP PC system, okay? The ATP, and you'll read that as you go through the chapter. The ATP, adenosine triphosphate, phosphocreatine system, is the immediate energy source that the body uses. Roughly up to about, it depends on who you read, up to about 10 seconds, 100%, 100% of all the ATP being produced or that's available is coming from this system. At up to about 10 seconds, roughly up to 15 seconds, that ATP PC system starts to lose its effectiveness for producing ATP for the exercise. The ATP PC system, as you can see, basically just conks out after about half a minute. Now, again, this is probably more like 40 seconds, 45 seconds, whatever the case is. That number is not what's critical. What's critical is this number right here, the 10-second one. So for the first 10 seconds of exercise, maximal intensity, right? Exercise that duration, you get on a treadmill and you start running as fast as you can. First 10 seconds approximately is going to be 100% of fuel usage is going to come from this system, right? And it's going to taper off at 11 seconds, 12 seconds, 13, boom. By the time 15 seconds rolls around, the ATP PC system, 20 seconds. By the time 30 seconds rolls around, the ATP PC system is basically used up. In other words, the amount of ATP that was that's already stored in the muscle now has been sucked up. The creatine phosphate molecules that are sort of re-energizing those ADP, converting them back to ATP, man, they're just conking out. They're done. So you're getting almost zero. You're almost getting zero energy, ATP, from this immediate energy system after about 30 to 40 seconds. It's no longer working to produce ATP. Well, long before this guy conked out, long before he conked out, the short-term energy system, see, there's a immediate, boom, first 10 to 12 seconds, 15 seconds, and then there is a short-term energy system. We call it anaerobic glycolysis, and that's what this line is representing. What you're seeing here is the anaerobic glycolytic system. Remember, first 10 seconds, the only major producer or available ATP is coming from the immediate energy systems, although you will notice that the long-term energy systems, the anaerobic oxidative phosphorylation system, does provide a tiny bit. Why? Because free fatty acids are always being used as a source of fuel in this case. But this chart, what this figure is showing you is that, of course, on the x-axis, we have the time, is that long before the ATP PC system, the immediate source of energy, starts to conk out on you, your body is already starting to utilize sugar, glucose, converted it into pyruvate. You'll read through that also, getting it to convert into ATP through this anaerobic system, right? Don't worry that they put the circle right here. That's what I'm trying to get you to understand, is just look at the line. Roughly at about, it depends on, again, who you talk to, right? Roughly at about 30 to 40 seconds, now your anaerobic glycolytic system becomes the dominant. You see 100%, right? It starts to produce a very high level. It maxes out roughly 30, 40, somewhere around there, 30, 40 seconds into it, okay? That energy system is maxed out at that time frame. Now, it will provide, and again, depends on the level of athleticism you have and, you know, the enzymatic capabilities of your particular energy system inside your muscles, 30 seconds a minute, all the way up to 2 minutes. Research has shown easily some folks, because of the capabilities of their enzymatic systems, are able to actually have glycolysis last upwards of even 3 minutes. In some cases, I've seen 3.5 upwards of 4 minutes. I mean, it's quite remarkable. Not that relevant. Point is that what this figure is showing you is that the glycolytic system maxes out and starts to shut down at roughly 3 minutes, 2.5 to 3 minutes, depending on how you read this chart. Well, that's about what? That's about 3 minutes right there. That's about 4 minutes right there. You see where I have my have that pointer. Roughly 3.5 minutes, something like that. The glycolytic system starts to taper off and lose its efficiency and effectiveness, because it can only do so much before the final long-term system of ATP production really starts to kick in and gain more and more control over over ATP production for longer duration activity. Okay, so that's where the blue line comes in. Please keep in mind, all three of these systems are generally functioning all the time. It's always I like to think of it as like a dimmer switch on a light. You have your switch that you can flick on and off. But energy systems are like dimmer switches. For those of you, you know what a dimmer switch is, right? Imagine 3 dimmer switches as and each one, the ATP, PC, glycolysis, and aerobic, right? Oxidative phosphorylation. So oxidative energy production, right? The electron transport chain, Krebs cycle, things like that. They all have their own dimmer switch. And as you crank up that dimmer switch, that's where the number goes from 0 to 100%. When I crank that dimmer switch all the way up, I'm at 100% of that particular energy system's capability to produce ATP. And then slowly but surely, I start to dial back the dimmer switch on the glycolytic system, right? And the dimmer switch goes down, ATP production. But the aerobic system, the oxidative systems, the production of ATP through the use of glucose that has been converted into acetyl coenzyme A through the Krebs cycle, produces NADH through the electron transport chain. You'll read all about that. And don't let that overwhelm you, by the way. That dimmer switch is really interesting, because if you see here, it starts low, but then as you continue this maximal energy output, it starts to crank up. It's slowly but surely, after roughly, I'm looking at what, 5, 6 minutes or 7, somewhere around there. That's where the aerobic production through particularly the electron transport chain, that's where the dimmer switch is cranked now, pretty much getting all the way to the top. And that's what's going to allow you to train, like a marathon runner at a, whatever that maximal intensity level is for the duration of your capabilities of continuing that energy output. So again, I wanted to make sure you understood the figure. Dimmer switch, whoop, dials down real low, right? The ATP PC system, because it's really just the innate supply of ATP, that's done, man, less than a minute. You're done with that system, whoop, dials it back down, but slowly, right? Slowly, well, not so slowly on the anaerobic system, glycolysis, but that dimmer switch on the glycolytic system, whoop, dials way up, and it reaches its max ATP producing output at approximately 30 seconds, somewhere around there. And it gets max output for approximately 2 minutes, minute and a half, 2 more minutes, right? Whoosh, and then it dials back down. Its ability, its efficiency to continue to produce ATP, whoop, drops back down. All along at this, while the ATP PC system and the glycolytic system are functioning and doing their thing, in the background is the aerobic system, the oxidative system, right? And that's guy is dialing his way up, dialing up, dialing way up until these other guys are, of course, that guy's done. This guy gets finished. He can't produce a ton of ATP. Boom, that aerobic oxidative phosphorylation. That's the system that comes into play and that takes over. Now, just as an aside, just so you know, this system right here, what do you notice? I'll wait while you think about this. What's different with the glycolytic system, or what do you see with the glycolytic system that you don't see with the ATP-PC system? What's the deal? That's right. This guy never travels all the way down to 0, does it? No. What happens when you're running a marathon and it's mile 15 and you're just cruising? I mean, you're really deep. You're deep in the aerobic, right? Phosphorylation. You are deep in that system. But then some guy comes up behind you, or girl, right? Comes up behind you and they start kicking it past you. What are you going to do? You're going to sit there and maintain your same speed? Oh, no. What are you going to do? You're going to kick it into high gear. Well, guess what happens? What allows you to kick it into high gear? This system right here. What will happen is you'll be able to access type 2X, type 2A, type 2X, right? Higher threshold, fast twitch muscle fibers that aren't doing a whole lot right now. And whoosh, you'll kick it back up a little bit and then it will go back down. So I thought you'd be interested in knowing that. I wanted to make sure you understood what this figure is basically telling you. And I do it because I've had lots of students tell me they don't understand figure 8.3. Can you please explain it? I'm hoping I did that for you. We'll continue through chapter 8, by the way, as the weeks go on here. And I'll just hit on certain elements because, like I say, this is actually fairly important for real world stuff. It really is. And then there's more figures. I'll give you a great example here, figure 810. And I'm not going to go into it now because, again, people get confused when they see it, but I'm just giving you a heads up. And please keep in mind, again, I hope this was helpful, but keep in mind, put your comments in below. And here's another thing I want to make sure you understand to make this more helpful for you from a study resource perspective. If you're in the Facebook group and you want to know something specific, post it so that is very specific. It's not that helpful. It's not that helpful if you're posting things that ask, does anybody have any study tips or whatever the case is? No, the study tips are already in here for you. You got to read the book, read, write, recite. Get into the study and actually post a question that says, I'm on page 233 and I'm looking at figure 8.4. Could somebody please help me understand what that means? Man, that's a perfect question to ask in the Facebook group or in a comment in the YouTube channel as well underneath this video. Try and be as specific as you can with the question, and then other students that actually know the material and want to kind of chime in will be able to help you. And I'm kind of going through the book now to give you another example of this. For instance, I'm just opening up to page 385 and I'm looking at figures 12.2, 12.3, 12.4. This is the static postural assessment. Look, if you want to post a question that says, can somebody explain static postural, that's fine. But what I would say is if you really want to get a good, firm answer to a question, you would post something like, I don't understand. Can somebody explain in figure 12.2 what this means? Or can somebody explain on page 285 or 385, whatever it is, this particular comment or whatever this means or whatever. If you could post that, that gives a lot more incentive for students to say, oh yeah, I've had the same issue. This is what I found, or this is how I studied that particular question that you're asking. It also allows us at Body Design University to put together a much more specific very targeted study, weekly study on that particular area. Just a little tip when it comes to posting questions into the Facebook group or asking questions in the comment section on the YouTube channel. If you do have questions, get them in there. Let me know. I'm more than happy to do a weekly study on it. Go ahead and subscribe to the YouTube channel. Of course, we would appreciate that. And notifications, obviously, on the bell, you can press that and you'll know when the new material is coming out. We here at Body Design University are focused on helping you pass this NASM, the NASM test on the first try. If it's not your first try, then of course your second or whatever try you're on. Just let us know how we can be of assistance. It's always a pleasure. Have a great weekend and a great week. And we'll see you next weekend. See ya. Bye.